All right, finishing this sheet up. Number 6 on this one is a question. It says a forensic investigator, blah, blah, blah. The main question here is you need to calculate the empirical formula. As a reminder, this is the one where I kind of gave you the acronym of please grab my radio. The job here is to take these percentages and figure out what formula would we have for a compound that was made of nitrogen, hydrogen, sulfur, and oxygen based upon the percentages that are in there. So we start with the percentages. We need to change that to grams. We need to figure out how many moles that is. And then we need to change that into a ratio so that we can figure out what's on here. All right, so I'm going to list these out. Hopefully this will not be messy. Nitrogen, oxygen, hydrogen. Do it in the order that's there. So nitrogen, hydrogen, sulfur, and oxygen. All right, so the percentages are there, 21.19%, 6.06%, 24.3%, and 48.45%. All that we do with these numbers is change them over to a gram because we're going to pretend that we had a 100-gram sample, because if we had a 100-gram sample, then we would have the exact gram amount as the percent tells us. Kind of combine these steps into one if you needed to. Great. Then our next job is we want to convert this into a mole. So we need to divide this by the molar mass. Just make sure I don't make any mistakes. Nitrogen's 14.01. Again, we're getting these numbers off the periodic table. Hydrogen's 1.01. Excuse me, sulfur's 32.07. And oxygen 16.00. We do the math on these, and we're going to get some moles. And so nitrogen ends up being 1.512 moles. I'm going to err on not rounding these. Hydrogen ends up being 6.00 moles. Sulfur, do the math, 0.757 moles. And oxygen is, I believe that's 3.028 moles. Again, this column basically tells us how many atoms of each one we have, because a mole is a certain number. So there's 6 moles of hydrogen, there's only 3 moles of oxygen. So basically, if you just look at the numbers, there's like twice as much hydrogen as oxygen. But to make this a little simpler, what we do is we want to divide them all by the same number so that we get them in a ratio that looks kind of nice. So we're going to pick out the smallest of the numbers that we have, which is 0.757. So we're going to divide all of these by 0.757 to change the ratio so that it's a little easier for us to see the numbers. And when we do this, we're going to get approximately 2. We're going to get approximately 7.93. We're going to get a 1. And we're going to get a 4. And 3 of these 4 numbers are pretty easy to see. This last one, we are just going to go ahead and round it up to an 8. And then we can, since these are nice whole numbers, and we can't really reduce the ratio, particularly because we got a 1 here. This is, these are the numbers that we need to put back into our formula. So the 2 is going to go here with the nitrogen. The 8 is going to go with hydrogen. The 1 would go with the sulfur, which we don't write. The 4 is going to go with the oxygen. So the empirical formula should look like this. Again, this is the simplest ratio of these elements once we get them there. So you have to go through these steps. Percent, change the percent to grams, change your grams into moles, use those moles to determine a ratio, and then from those numbers in the ratio, fill in the rest to be able to get your formula that you've got there. Okay, number 7, this posed a lot more problems than I thought it should have, because percent composition is simply looking at the part over the whole. Anytime we have a percent, we've got a part, we've got a whole, we need to multiply that by 100%. So in this one, our compound is D2E. Again, these are fictional elements from the periodic table. They're not on the periodic table. So D2E would be the whole, and if it's asking for percent composition of D, one of the most common mistakes people had was they just put this number in at the top for D, but in your formula, there's actually two D's. So it's not just D, it's actually going to be two of them. So that's kind of the bare bones of how you should have set the problem up, which means that we end up with 9.55, which is D, and there's two of them. And then we need to divide that by 9.55 times 2, which is the two D's, plus the value of E, which is 29.37. Okay. And then we need to multiply that by 100%. Get that into our calculator. We're going to get 19.1 over 48.47. Multiply that by 100%, and we should get 39.405. Again, some of us still struggle with the rounding here, but if we're doing two places past the decimal, I need those two numbers past the decimal, but I need to look at the third number to see if I round it. And since this is a 5 or greater, I do need to round this up. And when I round up, I'm only rounding the very last number. So I need to change this into 39.41. Again, it says include units, so this is going to be percent. It says include element, and it would be D. So sorry to kind of run out of room on you there, but we get 39.41% D to get that. Right. Number 8. This is a percent yield question. A lot of people just wanted to throw these two numbers in together and get a percent. That's not really how we do with percent yield, because these are actually two different substances. So you can't make a percentage out of those two numbers because they are two different things. One of them is H2CO3 and one of them is CO2. The question is, what is the percent yield of carbon dioxide? So just like in question 7, to get a percentage, we're going to need a fraction. And percent yield is the actual amount that we get divided by the theoretical maximum possible. The actual given is in the problem, which is 3.32. Sorry, 3.32 grams CO2. And we've got to find the bottom. And in order to find the bottom, that's where we have to use the other number. But what we have to do with this number is to say, if I started with 5.84 grams of, if I started with that many grams of, so I cut something off on this one with the formula. If I started with that many grams of H2CO3, how many grams of CO2 should I get? And that number ends up going on the bottom. So this is where we need to do Stoich problem. So again, we're going to be going from grams to grams. So grams, moles, moles, grams. Repeat in the bottom, starting one place over. Grams, moles, moles. All right. Do your substances. We're starting with H2CO3. And we're ending with CO2. Then the numbers, 5.84 is going to go in the beginning. This is our molar ratio. It's always 1 mole. I've already done the math to figure out the grams on this. Excuse me. So if you look up H, 2 H's, a carbon, and 3 oxygens on the periodic table, we get 62.03. Same thing at the end. This is our molar ratio. So 1 mole of CO2 has a mass of 44.01. And then this is going to come from our balanced chemical equation, which I think I somehow deleted off of this page. But in your balanced equation, everything has ones in front of it, which we can kind of ignore. So to go through this, take 5.84, divide it by that number on the bottom, multiply it by that number that's on the top, and it gives us about 4.14, and that's the number that goes on the bottom of the fraction. So then we take 3.32, divide it by 4.14, multiply that times 100%, and we end up getting 80.19%. Okay. So again, percent yield, The actual number is on the top. That's usually given to us in the problem. The theoretical number is on the bottom. We usually need to figure that out. And we can figure it out if we're given something in the reactant side. If we know how much of a reactant we have, we should be able to figure out how much of a product we have. That's the number that goes on the bottom for our fraction. All right, number 9 is another conversion question. There's a lot of words here, so of course kind of easy to get lost in this one, but if you read through everything, let's find our numbers and find our question. Here's our question. It says, how many grams of oxygen? Right. And then the number that we're given is 81.93 grams of water. So we're going from grams of water to grams of oxygen. That's all that we've got to do in this one. Just like previous question. Here we go. Grams, moles, 10 slow. Got to go slow. 10 grams, moles, grams. Same thing on the bottom. Grams, moles. And then we run out of room, so we don't do the last gram because that's what we want to get left with. Take our substance. So we're starting with the water because that's where our number is. We got H2O. Remember, that means if I go grams to grams, then I'm going to put water in the first 2 boxes on each row. And then I'm ending with oxygen. And then we need to put our numbers in the correct place. I got 81.93 at the beginning. Again, this is our molar ratio. So 1 mole of water is going to be, I think, 18.02. At the very end, 1 mole of oxygen. This is where some people made a mistake, is that it says oxygen in the problem, but notice in the formula it's O2. And again, if you labeled it out and wrote O2, that should tell you what the number should be here. The number is not 16, it's double that because there's 2 of them, so it's 32.00. And then our molar ratio are the numbers in front of oxygen up here, which is a 1, and the number in front of water, which is a 2. So we take our 81.93, divide it by 18.02, divide it by 2, multiply it by 32, and we get 145.49. And again, finishing it up, what 145.49 what? Again, there's your unit, there's your substance. And if you weren't sure about that, you could go back and read it in the question, but if you label out your conversions, you're going to have that there for yourself. All right, and then finally, the very last one. This was only a 1-step problem. A lot of people made this one harder than needed. Again, let's look through the question and see what we're looking for. It tells us that we've got 1.65 moles of oxygen. And the question says, how many moles of C4H6 would be required? So this is just a mole problem. We don't need to do the whole thing. Remember, the mole would be in the middle. So this is simply just a 1-step problem because we're going to start with moles and we're going to end with moles, which means that also moles ends up being on the bottom to cancel out because whatever we put in the upper left-hand corner is going to go diagonally down to the bottom. In terms of substances, keep it straight. We're starting with oxygen gas, which means that I'm canceling out oxygen gas, and then I'm turning it into C4H6. And then finally, let's get the numbers in the right place. I start with 1.65 moles. And then the numbers here, this is again our molar ratio, just like in question number 1. What's the number in front of C4H6? The number in front of C4H6 is 2. What's the number in front of oxygen? It's an 11. So now I've got all my numbers where they need to go. 1.65 times 2 divided by 11 equals, and it's going to be 0.3. But because the question says do 2 places past the decimal, you also want to throw a 0 on there. Make sure you're using your units. Again, the units of your answer should be right here at the end. Moles of C4H6. And if in doubt, go back to the question because the question you're answering is in the problem because it says how many moles of C4H6. So this is also what you're answering. You're telling me how many moles of C4H6. So if we start with 1.65 moles of oxygen, we would only need 0.3 moles of C4H6 for this to happen. We need more oxygen for that reaction to occur.